Hi there, welcome back to the Cosmic Classroom. We'll now talk about the lives of stars with low mass, and then I'll make another video to talk about life of stars with high mass, all right? So let's start with low mass. One very important thing to understand before we start talking about how stars change during their lifetime is to understand something that's called hydrostatic equilibrium, or we sometimes call it a solar thermostat. Okay, it's a process that allows the star to self-regulate. So if you please look at my first slide, what I'm showing here is that at every point inside the star, there has to be a balance between the pressure due to, sometimes the pressure is due to the heat, sometimes the pressure is due to the degeneracy pressure, whatever kind of pressure. But there has to be a balance between the pressure that wants to make the star expand and gravity that always wants to make everything come together and everything collapse into one thing. So at every point in this star, there is a balance between pressure and gravity. Pressure stops gravity and gravity stops pressure, and it's happening everywhere in the star. When this is happening, we say that the star is in equilibrium. Okay? So having understood that, let me start talking to you about what happens as the star reaches the main sequence. So the main sequence is a phase on which the star is in hydrostatic equilibrium. It's not collapsing or getting bigger. And what's keeping this hydrostatic equilibrium is the fact that there is fusion of hydrogen into helium in the core of the star. There is hydrogen all around the star, everywhere. The star is made mostly of hydrogen. Fusion happens only in the core because that's where it's hot enough for those atoms of hydrogen to bounce into each other, to get close enough to each other, to be able to fuse together and form a heavier element. So when this fusion happens, there is energy that's released, and this energy creates a thermal pressure that then balances gravity. So the star will live in the main sequence for most of its life. Our sun is in the main sequence now. It has been for the last 4.5 billion years. It will remain there for about another 5 billion years. While the star has hydrogen at the right temperature to fuse into helium, it will continue to do so, and the star will be pretty calm. It won't be changing very much. Now, eventually, the star will run out of hydrogen at the right temperature. It's not that it will run out of hydrogen. It has a lot of hydrogen around. It will run out of hydrogen in the core at the right temperature. So then what you have is a core that has helium, all that helium that was formed before, right? And more helium keeps being added to this core as there's fusion of hydrogen into helium. The core, as it becomes more massive, it actually becomes smaller and smaller. This is because the core is being held by the degeneracy pressure, which has to be the topic of another video, but just think about it as some kind of pressure, all right? So the helium core is becoming smaller and smaller and smaller, and the helium is accumulating in there. Eventually, the core collapses so much that it brings together some hydrogen that was around that shell, and the hydrogen is then hot enough to start fusing in a shell around the core. So if you look at this slide, you'll see that in this case there is a inert helium core. The helium is just there. It's not hot enough to start fusing yet. And there is fusion of hydrogen into helium in this shell around the core. And the process continues. More and more helium is continuously added to the core until you add enough helium, right? So the core becomes smaller, denser, hotter, and then you have enough helium at the right temperature to start fusing, right? So the helium, finally, when the core is very small, the helium starts fusing into heavier elements. The helium starts fusing into carbon in the core. And while this is happening, there is hydrogen fusing into helium in a shell around the core. Well, now you have two processes that are generating energy. And this star is growing because there's so much energy that's being generated. And one thing to remember is that the helium fusion doesn't start slowly. It starts very fast because the core is so compact that when the temperature is achieved in the core, it's achieved everywhere in the core. And the nuclear fusion of helium just skyrockets and becomes really, really high. So the star expands enormously. It becomes more luminous and it becomes bigger. As you can see here, the star is pretty big, right? So with time, the core, because so much energy, all right, so because so much energy was generated in this core of helium, the core finally starts to expand. There's so much heat that the core finally starts to expand. As the core does that, starts to expand, the rate of fusion decreases. All right, the rate of fusion decreases, and the star finds equilibrium again. It finds an equilibrium in which it's fusing helium in the core and fusing hydrogen in a shell around it. So you see that as the core expands, the fusion rate decreases, the star shrinks because there isn't so much thermal pressure, and the star achieves equilibrium again. That equilibrium won't last very long, but while there is fusion happening in the core, there is this equilibrium. So slowly, what happens is that we build a carbon core, a core that contains only carbon. And in low mass stars, that temperature never increases enough for carbon to fuse into heavier things. So that's already getting to the end of the life of the star because the core won't be able to fuse anything else. So for a while, you have a double shell burning. You have core of carbon that nothing has happened, a shell around that has helium fusing into carbon, and another core that has, and another shell, that has hydrogen fusing into helium. This double shell stage never reaches equilibrium. Okay, so the star starts to pulsate. Sometimes it creates too much fusion, and then it becomes very hot and it expands. And then because it cools down, gravity wins, and then it comes back again. So it keeps pulsating and pulsating until it finally ejects, and until it finally starts to eject its outer layers. So it gets rid of its outer layers. So this picture that you see here is from a star that has just died. The areas that you see around here are shells that have been ejected from that star as it was pulsating. And what you see right here in the center is what's left from that star. It's the very core of the star. That's why it's white. It's very hot. It's the very core of a star. The star lost everything that was around, and what's left is this core. This core is called a white dwarf. It's very dense and very hot. With time, the white dwarf will cool down and will become a black dwarf, and you won't be able to see it anymore. And with time, this nebulosity around the star will just move away and continue moving away until it becomes so thin that you cannot see it anymore. So you can only see it for a while. And that's the end for a low-mass star like our Sun. So that's it for that. Then let's talk about high-mass stars next time.